Mostly in chapter 4. Okay, we do a couple extra things. There's like these concept bites in your book, and we basically do that. So chapter 4, we're basically going to do everything in it. What does a quadratic equation look like when you graph it? Frankie? A parabola. Okay, so yes, we are learning about the parabola, or as one student once told me, the parabola. But it really is just a parabola. Yeah, I know. We're going to focus on kind of 3 parts of the parabola. What are some parts of the parabola that are recognizable to you that you feel are important and we should know them? Isabel. The vertex. Say it again. Axis of symmetry. Perfect. Nice. And x-intercepts. You guys got them all. Wonderful. Now, when we're graphing, we don't always use the x-intercepts. If someone just wants me to get a graph, sometimes that's handy, sometimes it's not. Does it even always have x-intercepts? No. So those come up a lot in a lot of contexts that we use the quadratic for, so it's important to know how to find them. We have to know how to find them. Do we always have to do them just because we're graphing? Not necessarily, okay? And we have to know what they're called besides x-intercepts. So all of these names can be used interchangeably, whether we're talking about a graph or an equation that is quadratic. So it's very important that you guys understand that if I put an equation in front of you and I say find the x-intercepts, you don't have to go to graph it to find the x-intercepts. There are ways that you can find the x-intercepts because x-intercepts are the same thing as solutions. Those are the same things as zeros. Okay, those are also called roots. So if they show you a graph and they say, what are the solutions? And you're like, I don't know, I need the equation. You don't, because solutions are the same thing as x-intercepts. And if you can see those on the graph, you have what you need. So these words will be used interchangeably in both graphical context and in the context of the equation. So we have to be okay with that and understand them in each situation as being interchangeable. Is that good with everybody? Okay. And then you guys mentioned 2 other pieces, the axis of symmetry. Remember where that is. And the vertex, which is really nice and slow moving on this PowerPoint. Yep, just wait for it. There it is. Okay, good? All right, so important things that we're supposed to know how to find. Now, depending on how the equation is written, some of these are simpler to find than others and have some really cool mathematical connections that maybe we remember from Algebra 1 or maybe we don't. Okay? So we're going to look at one way that it's written. Probably we're used to seeing in Algebra 1, and that is the standard form of the equation. So ax squared plus bx plus c. And when you go to graph this in its standard form of the equation, does anybody remember what they decided to do first? If I gave you an equation with numbers where a, b, and c are, okay, 2x squared plus x plus 5, how would you figure out how to graph it? Cassidy. Okay, so she said a really long formula. Do you guys know what that is? That is the quadratic formula. What does the quadratic formula do for you? So this could be useful in graphing. It might not be that useful, depending. Totally useful in solving for sure. What does the quadratic formula find? The x-intercepts, which are also called solutions, zeros, roots. Okay, so the quadratic formula could be used to find these. Yeah. But we don't necessarily need them to graph in this form. As a matter of fact, a lot of times when it's in this form, I don't actually solve it if I'm just trying to get a picture of what it looks like. But the reason that I thought it was so useful to remind you guys that one, the quadratic formula, so you remember the song or the poem or whatever it is, the flat-out memorization you did to get it. And 2, there's a really cool mathematical connection here to how we find some other things. If you were going to graph this, you do need some points on the parabola. You don't necessarily need these points. Okay, if we're creating the graph. What point, though, do you have to have on the graph in order to have an accurate representation of the parabola? Julie? You've got to have the vertex point. Does anybody remember from standard form a little formula that helped you figure out the axis of symmetry or the x-coordinate of the vertex? Isabel? There was like a fraction that had b in it. It's a fraction that has b in it. She's right about that part. All right, so let me ask you this. If these are the 2 solutions, where is the vertex in context of those 2 points? Max?
I was just going to say that the formula
Good. And I see that you're looking at something. How'd you figure that out, Max? Oh, you took the prep class. Oh, cheater. No, I'm just kidding. Not cheater. Very good. Very responsible, Max. Okay. So Max is right. It's negative b over 2a. Yeah. Good. So this is really cool because I think, and I might be wrong, and if I'm misjudging you, that's okay. Myself as an Algebra 1 student also. I think when we take Algebra 1, we feel like every formula, some really smart guy just wrote this thing down on paper and then everyone started using it, so that's how we figure it out. Okay? But really, there's all these really cool math connections about why these things work the way they do. The quadratic formula solves every quadratic because it really is just completing the square. We're going to see it again, but how many people have completed the square and found the quadratic formula? You have developed it and saw it. Okay, a few of us. Now, if then the quadratic formula solves every quadratic and the vertex is in between those solutions, if I want to find the number in between them, I do what Jacob said. I just average the two numbers that are there. So it's going to look really ugly for a second, just like a little side note here. But I want to add these two things together and divide them by 2. Give me just a second, because they're ugly. So, yeah. That's what I want to do, right? So it might seem a little overwhelming at first, but there's that guy. These fractions already have a common denominator. And what do I get when I add all this stuff together in the numerator? Julie? The rats cancel out. So there's only and 2 of them, right? And they're both negative? Uh-huh. So I have negative b over a divided by 2, and dividing by 2 is the same as multiplying by 1/2. And I have negative b over 2a. Oh, so they didn't just make up like, you know what? Let's just make up a math operation, how to find the center. No, it wouldn't work that way when we went to graph it if it wasn't right. So x equals negative b over 2a finds the middle of those solutions, which gives us our axis of symmetry. And how does that match up with our vertex point? How is our axis of symmetry related to our vertex point? I see Julie's hand. Oh, yeah. Ian.
The axis of symmetry, x.
Good. So that has to be the x-coordinate of the vertex, because the vertex can't be any more to the left or to the right of where the axis of symmetry is. And how do you get the y-coordinate that goes with that for the vertex once you know the x-coordinate? How do you get the y-coordinate for anything from a function once you know the x-coordinate? Okay, we're going to plug in what we get for the x into our function. And so I'm going to use some function notation to write that. If our function is called f of x, remember, when I want you to plug something in, I just replace the x with whatever you want to plug in. So you might not like the way the vertex looks here, and I'm not asking you to write it down, but we have to get really used to this complicated notation in our class. Wait for it, right? Okay. So here it is. The x-coordinate matches that. And remember, all this fancy stuff going on over here is just saying the y-coordinate of this point would be that number plugged into the function that we are calling f up there. Okay? If you have to write down plug in the x, then write down plug in the x. Okay? So again, if I was graphing this, I don't have to find the solution. So most of the time we memorize that negative b over 2a so that we quickly get the vertex point and where the axis of symmetry is. Once you have that point, you can plug in anything around that. Especially imagine if it didn't have x-intercepts. Okay? You'd have to plug in something else. The solutions wouldn't be able to help you. So oftentimes with this form, we're going to start with that to give us an idea of where this is and get this point. And then we're going to plug in whatever we want on either side. And we are going to do this later. This is like our overview, an idea of what's going to go on in the whole unit. Okay? As far as graphing goes. So another form that we might see this in, factored form. Factoring has been showing up on your weekly reviews, right? Yeah, those of you that let me say this. Those of you that are struggling with the factoring, we are not going to reteach factoring in here. I will be happy to help you individually. Okay? So you are going to do a factoring homework assignment. And it could show up on a homework quiz. We're definitely going to use it the entire unit. but I'm going to just have the people that don't know how to factor. How would you know if you don't know how to factor? If you're not getting that question right on the weekly review, or a friend is helping you with it every time you do it, you're not at the place where you can do it on your own yet correctly. You need to come in and make sure that we can get you everything you need for factoring. Okay? What is useful about having something in factored form? Try to think back to Algebra 1. I know it's hard. Julie?
There's no square.
Okay, so nothing's squared. It technically is squared if we multiply it out, right? But they've been like kind of separated, yeah. So what's useful? If I write, let me give you some numbers so you have some context instead of just like P and Q, okay? Let's say you have this equation up here. What can you do quickly? Why is already having it factored useful? Randall? Good. You can easily find the x-intercepts for plugging in 0 for y. Okay. I want to point out that we can't do this if this is any other number besides 0. I'll give you guys an example. Let's say I'm thinking of a number. You use two numbers to multiply to make the product. Okay. The product I'm thinking of is 2. What are the two numbers that must have been multiplied to make 2? Wrong. Ha, ha, ha. No, just kidding. Say another suggestion? 4 and 1/2. Okay, how many different combinations? That's not the combination I'm thinking of. But how many different combinations could you guys guess? Infinitely many. So I might tell you two things multiply together to make 2, and you might think, oh, this is easy. It must be 1 and 2. But really, there's infinitely many combinations. If I tell you that two things multiply together to make 0, there are still infinitely many combinations, but you know something. What do you know? Isabella? One of them has to be 0. It's the only number that has this property, right? This that you guys are talking about up here is called the zero product property. So the reason I'm making a big deal about this is because I see people set this equal to 5, and then they say, oh, so 2x plus 1 is 5, or x minus 5 is 5. And it's like, no, it doesn't work like that at all. It only works like that for 0 because 0 times something, if you're just doing a product, is the only way to get 0. So the only way this multiplication problem will turn out to be 0 is if one of the factors is equal to 0 or the other is equal to 0. Okay? And then I'm able to get my solutions. So yes, on this type of problem, I actually do enjoy getting the intercepts first because it's already laid out in a way that there's very little math for me to go through and find that piece of information very quickly. But if we do start with something like this, where we don't find the vertex first, and instead we find two other points, in this case our x-intercepts, how do you find the thing that's in between them? Because you do need the vertex to complete a graph. You don't necessarily need the intercepts. You need some points on the side. In this case, they're super handy, right? But you do need the vertex point to accurately represent the graph. So how would I find the vertex point if I was approaching this one and I have these two intercepts and I want to figure it out? Oh, what do you guys think? What would you do? Max? Did you put your hand up? No? Yes? No. What would you do? You have 2 points that you know are on your parabola, located there. You need to find the vertex. Well, you could find them in either order. Awesome. Okay, so if I want to find what's between these two things, this is how we got that little formula last time that we start with in standard form, right? That negative b over 2a became because it is the average of those quadratic formula solutions. In this case, that would actually be a super useful thing to do. And then again, how do we get the vertex once we know this? What did we say? So you have your axis of symmetry. How is that related to the vertex of the parabola? Yeah. Good. So that's the x coordinate on the vertex, and we would plug it in to get the y coordinate. And again, you're not going to like the notation, and it's super slow, but here's our plug it in to get the y coordinate kind of notation. Right, the last way that we're going to see our quadratic written while we study it in this unit is in vertex form. What does this look like? Looks like the graphs that we just did. Frankie?
Absolute value.
It looks just like the investigation we did with absolute value. So remember, what we've been focusing on with our greatest integer function and with our absolute value is putting numbers in these specific places and showing that they just take the most basic graph and then they transform it. So this is written in a way that A, H, and K aren't just numbers for me to use in calculations while I plug stuff in, but now they have a specific purpose. What kind of transformation is H going to cause if it's a number besides 0? Isabella? Good. Horizontal shifts. What kind of transformation is K going to cause? Frankie? Vertical shift. What is A going to cause? Julie? Or a compression, either way, and if it's negative, even a reflection, okay? And in our class, the added part is that we are going to see what would happen if there was like a B value there in front multiplying X, okay? Regular Algebra 2 doesn't do that. They save that for pre-calc, but congratulations, we do it in here. Yay, right? Okay. All right, so very slowly. Like you saw with our investigation, since the H and the K are the only things that affect the vertex point, those shiftings find our new vertex. Remember when you guys were graphing absolute value and you would use the H and the K as the first point that you put on the graph? Okay. Now this automatically also tells us something else about our parabola. What else does it tell us? Isabel? Good, the axis of symmetry. If we know the vertex, then we know the axis of symmetry. Now, to find solutions, you would still just have to find solutions, okay? If that's what you wanted. If that's not what you wanted, then you could get any other point. What did we do with absolute value? We graphed the vertex, and then what other piece of information told us how to get the points to the left or to the right of the vertex? Natalie? Good, the A value. Now, with absolute value, it was like slope. We literally just said what it said. Here, you can't do that because if you kept going the same rise and run, you would not get a curve, right? You would get a line. But the A value plays the same role, and we're going to learn how to stretch and compress it properly. Okay? So is this okay for an overview of kind of how all the parts of the stuff is related? Hopefully you saw something cool, like they didn't just make up that negative B over 2A formula. It came because it makes sense with the quadratic formula and stuff like that.